Hello students, in this session we are going to discuss about the 10th science 1 chapter 1st gravitation, and in this chapter we will discuss about the Kepler's laws and Newton's universal law of gravitation. As we studied before, the first law of Kepler's first law was the orbit of a planet is an ellipse with the sun at one of the foci. So now let's study the second law of planetary motion. Just observe the figure on right hand side. The sun is given and the planet is rotating in elliptical orbit. Okay, now planet moves from P1 to P2. Okay, so it covers a distance area 1 and in time t. Also it covers a distance, this planet covers the distance from P3 to P4. That means it covers the area A2 in time interval t. That means here we can say that area 1 equal to area 2, and also it takes the equal time interval t. Also you can observe the figure given below, that sun is given how planet covers the distances in equal time. Okay, so how to define the second law of planetary motion? The line joining the planet and the sun sweeps equal area in equal intervals of time. Kepler's third law. First observe the three figures. In first figure they are given that the orbits are ellipses, and this was the first law of planetary motion. That means sun is there and the planets orbits with the sun in elliptical orbit. Okay, now in second figure the planet revolves in an elliptical orbit and it covers the equal area in equal interval of time. That means the line joining the planet and the sun sweeps equal area in equal interval of time. So this was the Kepler's second law of planetary motion. Now let's study the third law of Kepler's. Now in third law, suppose that the r is the average distance of a planet from the sun and t is the period of revolution. Period of revolution, that means the time is required for to complete the one revolution. And here we can say that t square is directly proportional to the r cube. That means the square of its period of revolution around the sun is directly proportional to the cube of mean distance of a planet from the sun. That is, t square is directly proportional to r cube. So t square upon r cube equal to constant, call it as k. Okay, this was the Kepler's third law, but he had no explanation so as to why planets obey this law. So we will see after then how the Newtons in the formulation use this of his theory of gravitation. Let's know about how Newton used the Kepler's law in his law of gravitation. Okay, suppose that the two objects A and B, they are placed at a distance d and they having masses m1 and m2 respectively. Then every object in the universe attracts every other object and they have some with a definite force, and this force is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. That means here we can write F is directly proportional to m1 into m2 upon d square. Okay, so just replace this proportional sign, we get F equal to capital G into m1 m2 upon d square. Here capital G is called as a constant of proportionality. That means it is called as a universal gravitational constant. Okay, also note that here if mass of the object is doubled, then the force between the two objects also doubles. Okay, also if the distance is doubled, then force decreases by the factor 4, because see in the formula F equal to G m1 m2 upon d square. So if we take a distance is a double, then we are taking the square. Okay, That means F is inversely proportional to the square of the distance. That means if distance is double, then force will decrease by a factor of 4. Okay. If two bodies are spherical, then the direction of the force is always along the line joining the centers, and that is taken to be as D. And if the bodies are not spherical, then direction of force is along the line joining their centers of mass. Okay. So let us find the SI unit of G. So how to find? Formula is that F equal to G into M1 M2 upon D square. So we get capital G equal to F into D square upon M1 M2. Okay. So what will be the SI unit of G? Here we know that the SI unit of mass, okay, it is taken to be as a kilogram. Okay, so M1 into M2, so we will get kilogram raised to minus 2. Okay, now the SI unit of F is a Newton, so we get a Newton into kilogram raised to minus 2 into D square. D is a distance and it is measured in meter, so we will take a meter square. So what is the SI unit of G? G equal to, we will get the unit of G as Newton into meter square into kilogram raised to minus 2. That means Newton m square per kg square or into kg raised to minus 2. This is the unit of capital G. Let's know about the uniform circular motion magnitude of a centripetal force. Okay, as we studied earlier that the circular motion and the centripetal force, how they are related. So here consider an object moving in a circle with a constant speed. We have seen earlier such that a motion is such motion is possible only when the object is constantly acted upon by a force directed towards the center of the circle. So this force is a centripetal force. Centripetal force means center seeking. The force is towards the center. Okay. So let m be the mass of the object, v is the speed, and r is the radius of the circle. Then it can be shown that the force F equal to mv square upon r. mv square upon r. Okay. Here the speed of the planet can be expressed in terms of the period of revolution. Okay, so we know that the formula of speed is the distance traveled upon time taken. So here the distance traveled by a planet in one revolution is just, we can take the perimeter of the orbit, and we know that the formula of perimeter is 2 pi r, and r is the distance of the planet from the sun, and t is the time period of revolution. So v equal to distance traveled upon time. So v equal to 2 pi r upon t. We know that F equal to mv square upon r. So just replace the value of v by 2 pi r upon t. We get 4m pi square r upon t square. Okay. Now we know that what was the Kepler's third law? Kepler's third law is t square upon r cube. That means square of the time of revolution is directly proportional to the cube of the distance of the planet from the sun. Okay, that means t square upon r cube is a constant k. So let us just multiply and divide this equation 4m pi square r upon t square, multiply and divide by r square. Okay, so by multiplying we get 4m pi square r cube upon, by dividing we get r square t square. Okay, so we get 4m pi square. As we know that by the Kepler's third law, t square upon r cube is a constant. So here we can write r cube upon t square equal to 1 upon k, 1 upon constant. So we get the new equation as 4m pi square upon k. constant into r square. Okay, now we know that m is the mass of the planet and that is a fixed, that is a constant. So we can say that 4m pi square upon k, this quantity is a constant. Okay, therefore we get f equal to constant multiplied by 1 upon r square. That means f is directly proportional to the square of the distance. Okay, that means Newton concluded that the centripetal force, which is the force acting on the planet, is responsible for its circular motion, and that must be inversely proportional to the square of the distance between the planet and the